All right, guys. So this is going to be the video, chapter 5 video on Lewis structures. You should have watched the other video first on bonding before you get to this one. Okay, so let me pull up the slides where we left off last. We discussed ionic and covalent compounds. Now we're going to move on to a bonding model that we use very regularly in order to um, uh, represent compounds and know how to draw them. So it's going to be called Lewis structure. But let me first tell you guys what models are and what are the advantages and disadvantages of those. So since we can't observe the atom directly and electrons and what really is going on in bonding, we have to use models in order to visualize and explain and also predict chemical changes. So we do our best, without having actually seen the atom. So all of these models are supported by experimental results and evidence. We've designed a lot of experiments in the last hundreds of years in order to, bolster these models and make sure that they're, as effective as possible and as close to the truth as possible. But of course, we don't know for sure, right? And so that's why we have multiple different models in order to explain some of the same things, because all of these models have boundaries and they break down after a while. So then you need another model. You need to bring another model in order to explain what is going on. So that's sort of disadvantage, right? But the advantage of models is that we've been using them and it's been working for us. Look at the world around us. Models have helped us to shape our world. And so that's the reality. That's just how it is. And so one of the characteristics of models is that it's going to change over time, right? Because it does have boundaries and it will break down. But using different models to explain one thing is going to be, much better than, just using one model. So it's, that's the reality. And so we use multiple models for bonding, for example. So the valence bond model tells us that only the highest energy electrons are the ones that participate in bonding. And the core electrons, all the electrons that are closest to the nucleus, they just don't do anything. They just sit there. They do not participate in bonding. And what else the valence bond model tells us is that it's the unpaired electrons that are going to be participating in bonding, not the ones that are paired up. Okay, so those are really the two biggest assumptions of the valence bond model theory. Okay, so here's an example, and let me actually go to the board for this. This is going to be easier to envision. So let's say that, if we look at why two hydrogen atoms bond together, okay, we can explain this by using the valence bond model. So we would think about how many valence electrons hydrogen has. Now, valence electrons are the outermost electrons of an atom, and those are the electrons that participate in bonding. To find out the valence electrons of an atom, it's actually very easy. All you need to do is go to your periodic table and let's see if I can find one here. Okay, go to the periodic table and you just look up at the group number. That's the column number. Okay, so for example, if you look at hydrogen, hydrogen is in group 1A. So it only has one valence electron. Okay, but let's say if you look at fluorine, okay, you see that fluorine is in group 7A. So fluorine has how many valence electrons? 7. Okay, and all of group 7A elements have 7 valence electrons. So even chlorine has 7 valence electrons. Bromine has 7 valence electrons. Group 6A, all of those elements have 6 valence electrons, right? So again, just going by group number. So oxygen has 6 valence electrons. Sulfur has 6. Selenium has 6. Okay. Obviously, the noble gas has 8 valence electrons. Okay. And so remember, that's everybody wants to be like the noble gas, so everybody wants to have 8 valence electrons, right? And so that's why earlier when we did ionic bonding, group 7A is always negatively charged because it wants to gain 1 electron to get 8, right? But if you're in group 6A, then you want to gain 2 electrons to get 8, and so you become 2 minus and so on. Okay, so group 5A, 5 valence electrons, so nitrogen is 5, phosphorus is 5 valence electrons, group carbon is 4, okay, and so on. So quite easy to see there. Okay, and so what I'm going to show you now is how to do the electron dot symbols based on the valence electrons. So if we go back to hydrogen, right? Remember, the hydrogen has 1 valence electron, so you're going to draw just a dot. Okay, so that's why we call this the electron dot structures. And then we can draw another hydrogen with its 1 valence electron. Okay. And so why do these come together is 2 electrons will make a bond. So basically this hydrogen, right, comes together with this hydrogen's electron gets donated to that one, and this one donates its electron to that one. So they share, right? And so 2 electron makes a bond, and that's how H2 element is formed. Okay. Now, if we go to something like HF, we can see the same, similar, okay? You see how valence bond theory works. So hydrogen with its 1 valence electron, fluorine has 7, right? And this is how you should do electron dot structure when you have multiple. You should divide up the atom into 4 quadrants, left, right, up, down. Those are the 4 quadrants. And you're going to fill each quadrant first with just 1 electron before you pair it, okay? So kind of like Hans rule, right? Well, don't be the creepy person on the bus. So 1, 2, 3, 4. Okay, now after I have 4, then I can pair. And it doesn't matter where I go, okay? As long as I have 3 lone pairs and a single electron, right? For a total of 7, right? So notice I went 1, 2, 3, 4, 5, 6, 7. Okay, so what we see is that the unpaired electron of fluorine is the one that's going to make a bond because these are already paired up, right? That's part of the assumption of the valence bond model. So that means that this unpaired electron of hydrogen will pair with the unpaired electron of fluorine, and that's where they're going to make a bond. Again, 2 electrons equals 1 bond. Okay, now as you get more advanced, okay, and you should, you know, be advanced here pretty quickly because this is pretty easy to see, right? Don't even show the dot. So you're just going to show the bond, and you know that that is implying electrons there, right? So don't even show the dots, just show the bond. Okay, it just looks a lot cleaner. Okay. So now I know that your book does like to use the dots a lot, but I encourage you to just go straight to the bond. Okay. We can do another one. So if we were to draw, you know, just quickly drawing like H2O, this is how it works because you have oxygen, and oxygen has how many valence electrons? 6. So 1, 2, 3, 4, right? 1 on each side before you pair up. 5, 6. So once you do 6, you see that, oh, oxygen has 2 unpaired electrons. That means that oxygen is going to want to make 2 bonds in order to pair those up. And so hydrogen, remember, has its 1 electron, 1 valence electron, okay? And that's going to be the one that's going to pair up with the oxygen. And so that's why H2O looks like this, okay? So the electron dot structures can really help you figure out how to draw these molecules. Okay. And now I want to show you something even cooler, some bonding patterns that you're going to see very often when drawing Lewis structures. And then we're going to go into really full-blown drawing any Lewis structure when you're giving a chemical formula. Okay. All right. So please take notes with me, and I hope you've been taking your notes as you're watching these videos. Make sure you're taking notes, but let's do this exercise together. Excuse me. Okay, so the exercise we're gonna do is we're gonna see how different elements of period 2, right? So that's row 2 of the periodic table. Forming bonds with hydrogen. Okay. And we'll start with boron. And then we'll go all the way to fluorine. So remember, always valence electrons are the ones that are involved in bonding. So we're going to do electron dot for boron first. That's 3 valence electrons, right, everybody? So you're going to do 1, 2, 3. And then hydrogen. So since boron has 3 unpaired electrons, and we said it's the unpaired electrons that make a bond, right? It's going to want to make 3 bonds. So that means we're going to need 3 hydrogens, right, in order to do it. So how's that going to look like? E with 3 hydrogens bonded to it, right? And each of these dots represents the electron, right? Boron brought its 3 valence electrons. Each of the 3 hydrogens brought 1, and then we form BH3, okay? So notice the features of BH3. It has 3 bonds and 0 lone pairs. I'm gonna represent lone pairs with LP, okay? Now let's move on to carbon. If you look at the group number, right, column number, carbon is in group 4A, so 4 valence electrons. Again, 1 on each side first. So if you do that, you see that carbon has 4 unpaired electrons, right? Which means carbon will want to make 4 bonds, which means we have to introduce 4 hydrogens. So what is that going to look like? Okay, each of hydrogens 1 electron will pair with carbons. So you get this CH4, 4 bonds. And again, you don't see a lone pair, so 0 lone pair. Okay, we can keep going. Nitrogen. Now, 5 valence electrons, right? So notice how I'm going to do it. Remember, 1 on each side first before you pair. So I just have 4. Now this one is going to be my 5th, right? And you can pair it anywhere, right? Doesn't matter. So what do I see though? I have just 3 unpaired electrons now, which means nitrogen is only going to want to make 3 bonds. So I only need 3 hydrogens. So that's going to be NH3, right? And there's a lone pair left over on the nitrogen. Okay, so NH3 has 3 bonds and 1 lone pair. Okay, so what we're seeing here is the reason why things are the way that they are. These compounds are the way that they are. NH3 is NH3 and can only be NH3 as the compound, not NH2, okay? Or not NH and not NH4 due to its number of valence electrons, okay? Let's move on. See, oxygen should have 6 valence electrons, right? So that's going to be 1, 2, 3, 4, 5, 6. And so once we do the Lewis dot, we see, oh, it only has 2 unpaired electrons. So it's only going to want to make 2 bonds. So that means we only need 2 hydrogens. Um, so what do we see? Right, that's where the hydrogens are going to come in. Okay. So here we have 2 bonds and 2 lone pairs. Okay. So notice nitrogen will want 3 hydrogens around it. The oxygen just wants 2. Okay. And it has 2 lone pairs. Okay. Lastly, fluorine, that's 7 valence electrons. 5, 6, and 7. Plus 1 hydrogen. So once you do this, you see that there's only 1 unpaired electron. And that's why you only bring in 1 hydrogen. So what we get is HF. 1 bond and 1 lone pair. Okay. 1 bond and 3 lone pairs. Sorry, we forgot these 3 here, right? On the fluorine that was there earlier. So we have 3 lone pairs. Okay. All right. So we completed period 2 bonding with hydrogen. You guys see a pattern here. You see that when we add these across, we always get 4. Right? 3 and 1, 2 and 2, 1 and 3. They're all equal to 4. And these are all pairs, either bonding pairs or lone pairs. So 4 times 2 is equal to 8. Okay, so everybody wants the bond so that they will have 8, right? The central atom should have 8 valence electrons. And why 8, guys? Because it wants to be like the noble gas, right? And so the number of valence electrons for each element guides its bonding pattern, okay? So what you will see for period 2 elements is that carbon will always want to make 4 bonds and have 0 lone pair, okay? Nitrogen will always want to make 3 bonds and only has 1 lone pair, okay? Whereas oxygen will want to make 2 bonds and have 2 lone pairs. And hydrogen, fluorine, will always want to make 1 bond and has 3 lone pairs. Right? That's the bonding pattern that you guys will see over and over again. And you can actually extend this to other elements too. This will always happen for period 2, no exceptions. Now for other period, like period 3 elements, you will have some exceptions, but you will see that this is very common. Okay, so even in something like sulfur, like H2S in this molecule, okay, again, sulfur has 6 valence electrons because it's in oxygen's group, right? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, so it has 2 unpaired electrons, and that's where the hydrogen is going to go, right? Actually, let me switch it to that because I don't have room. But you see, it's the same bonding pattern. Sulfur likes to make 2 bonds and has 2 lone pairs as well because it's in group 6A. Okay. If I do HBr, similar deal. Br has 7 valence electrons, so it just has 1 unpaired electron, which will bond with the hydrogen, right? So bromine being in group 7A also likes to make 1 bond and has 3 lone pairs. That's sort of usual bonding pattern that you're going to see. Okay. So it's going to be really helpful to keep this in mind when we go to the next part, when we draw Lewis structures, to check to see that the bonding patterns that you see make sense. Okay. All right. All right. So let me show you guys something. When we get to Lewis structure, which we're gonna do next, there are steps for doing Lewis structures, and it's on Canvas. So let me show you guys that. Okay, so here are the steps right here. Drawing loose structures for covalent compounds. So it's a step by step, and you should download this document and kind of have it alongside the lecture so you can follow each step, and so you know exactly what I'm doing for each step of drawing the Lewis structures. So there are 7 steps. It seems complicated, but I'm really breaking it down into the smallest possible steps so that you guys can follow. After a while, when you do, of doing this, you're gonna see that it comes second nature, and you're gonna not have to look at these steps, right? Because you're not gonna have these on the exam, right? So you should do it until it becomes second nature to you. So you're not gonna have to look at it, right? Okay, so step 1, when you're given a chemical formula, you're going to add up all the valence electrons for the entire molecule, right? So you know how to do valence electrons now. Look at the group number. You're going to add it up for each element and then sum it all up. Then in step 2, you're going to determine which is the central atom. And sometimes there are multiple central atoms. So it's just going to be case by case. But the best way to do that is pick the atom. The central atom should be the leftmost from the noble gas or the least electronegative atom, right? So leftmost from the noble gas, and now with the exception of hydrogen, because hydrogen is very far to the left of the noble gas, but hydrogen only has 1 valence electron, right? So that means hydrogen can only ever make 1 bond. It can't make more than 1 bond. So it can never be the central atom, okay? So don't even try to put hydrogen as the central atom. You're going to pick the leftmost from the noble gas, okay? Then in step 3, it says distribute the surrounding atoms evenly around the central atoms. In step 4, draw 1 bond only from the central atom to each surrounding atom. Count how many electrons are used up so far and how many are left. That's step 5. And then in step 6, very important, it says distribute the remaining electrons as pairs. Okay. And how are you going to do it? From the outer atoms and then into the inner atom, ending up with the central atom. Okay. To do what? To fulfill that octet. Remember the 8 that we kept seeing? That's the octet, right? Because they want to be like the noble gas. And it says if you need to make a double bond in order to fulfill octet, then go ahead and do that. And then check for octet again. If it's still not good, then make a triple bond. So don't rush, right? Always at each step, check to see if octet is fulfilled, and then you add another bond. Then step 7 says check to make sure every atom is happy. And when I say happy, it means they have octet and that they fit their bonding patterns that we just talked about, right? Do the bonding patterns make sense? Okay. Okay, so let's go back to the board and have those steps out in front of you, everybody. And we're going to do this together, all right? I'm going to start simple. Simple would be compounds with just single bonds, right? Nothing fancy and then we can graduate to double and then triple bond. So first example, let's do CH2F2, everyone, okay? Now, the first step it says, right, I'm actually going to label each step so you guys know exactly where we're at along that sheet and what I mean, right, by each step. So step 1 is adding up all the valence electrons total for the compound. So carbon will have 4, right? Hydrogen has 1 valence electrons, right, guys? But there are 2 of them, so 2 times 1, right? Fluorine has 7 valence electrons, right? Remember, looking at the group number. So that's 2 times 7 for a total of 14, 16, 20 valence electrons. Okay, now that's step 1. I'm going to label it, okay? Step 2, it says, pick your central atom. There are 3 atoms here, carbon, hydrogen, or fluorine. Remember, hydrogen can never be in the center. So it's just between carbon and fluorine. Well, which one is to the leftmost of the noble gas? Carbon. Yep. So carbon's going to be in the middle. And that's step 2. Okay. All right, let's go to step 3. Notice I'm really doing this, very fine steps. Okay. So making sure that you guys can follow. So 3 it says, now you're going to distribute the remaining surrounding atoms, right? The surrounding atoms are the rest of them, 2 hydrogens and 2 fluorine, evenly around the carbon. So we had this picture earlier. Evenly means you don't want to clump them like that, right? Remember that these have electron clouds, and the electrons are negatively charged. They repel each other, right? So you're not gonna want to draw it clumped up like that. Think of like a bonfire, right? The central atom's the bonfire, and everybody is going to spread out evenly around the bonfire. So you're gonna do that, right? Okay, and that's step 3. In step 4, it says draw a single bond only between the central atom and all of the surrounding atoms. Okay, and so we had this before. Okay, and remember, it doesn't matter where you put it. You could have put the hydrogens here too and fluorine, so it really doesn't matter. Okay, as long as you spread it evenly. So step 4 is this. It's saying just draw single bonds to each atom. Okay, single bonds. Remember, each bond is 2 electrons. So that's why in step 5, right, you need to count how many electrons are used by drawing those bonds. That's 4 bonds, so that's 8 electrons used. And how many are left? Well, subtract 8 from 20, and you're gonna get 12. Okay, easy. Okay, then step 6, it says you're gonna distribute the 12 electrons left, the ones remaining, as pairs. Okay, you're gonna do it from the outside atom to the middle. So always outside and then inwards. So here's the picture we had from step 4. Okay, now we're gonna take the 12 electrons and put it on this picture. No more, no less. That's very important. So hydrogens don't need it because hydrogen's already happy. The closest noble gas to hydrogen is helium. Agreed, everybody? And helium only has 2 valence electrons. So here, hydrogen already has 2. 1, 2. Okay, here hydrogen has 2 as well. Okay. Okay, so now we go to fluorine. Fluorine has 1, 2, but it needs 8. So it needs 6 more. If you're gonna do this as pairs, that's 3 pairs, right? Remember, you always need to distribute the remaining electrons as pairs. So that's 2, 4, 6. So 3 lone pairs for the fluorine, and that makes 8. Okay. So again, let's, make sure that you guys can know how to count for octet. When you count for octet, count the shared electrons. Count all shared electrons. Okay. So remember that this bond was, is like this, right? But we're not gonna do that normally, because we're just gonna make a bond. It looks much cleaner. It look less kindergarten, So we want to look cool. We don't always want to put the dots in there, but we know the dots are there, right? And so that's what we're counting. The shared electron, the fluorine is actually sharing its electron with carbon, and carbon is sharing its electron with fluorine. So what we're saying is when we're counting for octet, we count all the shared electrons. So fluorine counts 1, 2, 3, 4, 5, 6, 7, 8, and the electron that it shares, right? That carbon shares with it. Okay, so this electron as well. So that's how you get 8. Okay. Now for this fluorine, same thing, right? Right now it has 1, 2. It needs 8, so you need to put in 3 pairs. Always distribute the remaining electrons as pairs. 2, 4, 6, 8 as your bond. Okay. So again, counting for octet, 2, 4, 6, 8. Okay, so fluorine's now happy. The only atom that we have not checked is carbon. So check carbon. 2, 4, 6, 8. Carbon has 10. That's step 7. Checking everybody has octet. So once you have that, guess what? You're done with your Lewis structure. Very simple, right? That's all there is to it. So now we're just gonna practice a whole bunch of them, right? And sometimes you're gonna have to make double bonds and triple bonds in order to do it, but you see all the steps now, right? Not complicated. You just want to make sure you follow each step. Don't skip any. Okay, follow it to the T. Our next example, PCl3. So valence electrons first. Phosphorus is 5. Okay. Plus chlorine is 7, but you got 3 of them, so 3 times 7, total of 26 valence electrons. Agreed, everyone? Okay. Then, again, that's step 1. Step 2, deciding the central atom. Between phosphorus and chlorine, which one is furthest left of the noble gas? It's gonna be phosphorus. That's your central atom. Step 3, you're gonna take the chlorines and spread it evenly around the bonfire, right, of phosphorus. So evenly is like this, like a triangle, right? Don't clump them together. Okay. And step 4 is you're gonna make single bonds only from the phosphorus to the chlorine, right? Don't rush, single bonds only. Step 5, you're gonna count how many electrons are used. Well, you made 3 bonds, so that's 6 electrons used. And how many are left? Well, 6 from 26, right? We had 26 total, so now we have 20 electrons left. Okay. In step 6, we're going to take the 20 remaining electrons. We're going to put it into your picture. Remember, distribute the remaining electrons as pairs, outside to inside. So the outside gets it first. So we have this earlier. And so each chlorine, right, is already making 1 bond. That's 2 electrons. That means they only need 6 more electrons to get octet. 6 divided by 2 is 3. It's 3 pairs. Remember, it has to be as pairs. So 3 pairs on each of the chlorine to make octet. All right. And is that 20? Well, let's count. Well, how many dots have I made now? Right. I can't put any more dots on these because I'm going to screw their octet. But I know that I put 6 dots in each chlorine, and there are 3 chlorines, so that's 18 dots. But I should have had how many dots? Because I had 20 electrons left. So I have 2 dots left. Where am I going to put them? On the phosphorus. Doesn't matter where, right? Just wherever you have room, you're going to put the lone pair on the phosphorus. So see what I mean, or see what step 6 means, is you distribute the electrons from outside inwards until you end at the central atom, right? Those are the last electrons are going to go there. Okay. Important here is don't add less than 20. Don't add more than 20. It has to be exactly how many electrons are in the structure, should be on your picture. Okay. So if you really count all this again, it should be equal to 26. No more, no less. Got it? Okay. So then step 7, we're going to check our octet. Let's see. The chlorine I know are happy because we made them happy, right? We purposely did. But we need to check phosphorus. Is it happy? 2, 4, 6, 7, 8. All right. Everybody's happy. And that's your structure for PCl3. I usually circle it just because there's a lot going on, right? So always circle your final answer. It's going to help me grade. It's going to help you. It's going to help me. Okay. Let's move on to double bonds. First example, CO2. Valence electrons first. So carbon is 4 plus 2 times 6. 6 for oxygen, right? So that's 16 valence electrons. Central atom, well, between carbon and oxygen, carbon's furthest left of the noble gas. Okay. And then what do we do next, guys? Distribute the remaining atoms, right? The surrounding atoms evenly around the carbon. Well, you only got 2 oxygen, so just put them, opposite each other, as far away from each other as possible, right? And then the next step will be what? You now try not to look, right? Try to remember single bonds only, right? And then count how many electrons are used. How many are left? 12, because we had 16 total, right? So how are you going to put 12 on the CO2? Remember, outside in. Each oxygen is going to need 6 again, right? Because it only has a single bond right now. That's 2 electrons. So it's going to need 3 lone pairs. right? Notice it's like the same thing every time. It's 3 lone pairs. Boom, everybody, right? 3 lone pairs, because that's what's going to get you octet, right? So 2, 4, 6, 8, 2, 4, 6, 8. Okay. Now, how many dots have I made? 2, 4, 6, 8, 10, 12. So I've made enough dots. Okay. So now I'm going to check octet. I know my oxygens have octet because I made them. So let's check carbon. 2, 4. We're not done with the structure, right? Because the carbon does not have an octet yet. So how are we going to rectify this situation, right? Notice that in step 6, it says you could put a double bond to make it an octet, right? So how should we do that? If we just put a double bond like that, because what's wrong now? I added 2 additional. I can't have 18. I can only have 16. So you can make a double bond by moving electrons. You cannot add it, but you can move electrons that are already there. Okay. So where are the electrons already there? Well, you have a bunch of dots here, right? So remember, 2 electrons make a bond. That means you can move lone pairs to make a bond. And it doesn't matter which lone pair you use. Let's use the left oxygen first because it has 3 lone pairs. Let's take this lone pair and move it down here for a double bond. That means on the left side, it's going to look like this. This oxygen now only has 2 lone pairs. The other lone pair went down to make a double bond with carbon. On this side, it hasn't changed. So this oxygen still has 3 lone pairs. So now you check your octet again. You realize, oh, look at that. I made this oxygen is still octet. This oxygen is still octet. And I made it better for this carbon because now it's 2, 4, 6, but it's still not octet. So what should we do? One more time. You can show it, right? Show with an arrow that this lone pair is going to come down for a double bond. This is visually mainly for you because you need to keep track of where your electrons go. So, try to be like really diligent with doing that because that's going to help you. All right. Because you're going to see, oh, that means I have a double bond here, double bond here. But this oxygen now only has 2 lone pairs and not 3, right? Because one of them already went to make a double bond. It's a way of accounting for where your electrons are, which can get really confusing when you get to, the more complex structures. So I really highly recommend doing the way that I'm showing you guys, right? All right, so now check again for your octet. Oxygen 2, 4, 6, 8 still has octet. This oxygen 2, 4, 6, 8 still has octet. Carbon, let's see it. 2, 4, 6, 8. Carbon is now good. Check octet and circle your answer. So that's CO2. Now you can see this structure has a double bond, right? All right, let's do H2CO as our next example. That's an O. Hydrogen is 1 valence electron, but you got 2 of them, so 2 times 1. Plus carbon is 4, oxygen is 6. All right, just looking at the group numbers. 10, 12 valence electrons total. Which one's your central atom? Looks like carbon, right? Leftmost of the periodic table. And then you're gonna put the surrounding atoms evenly around carbon. You move it down here. So it doesn't matter how you do it, right? As long as you have it all spread out, right? Remember, it's like a bonfire, and you spread everybody around the circle. Okay, so now single bonds only. It's our next step. And then you count how many electrons used. 2, 4, 6. On the left, 6. And then you're going to put the 6 electrons on your picture. How? Outside in. Do hydrogen need it? Sorry, making 1 bond, 2 valence electrons. It's good. Oxygen needs it though. So put 3 lone pairs there to get oxygen to be octet, right? 2, 4, 6, 8. And I've used up my 6 dots. So I can't put anything else on. But I realized, okay, when I check carbon, it's 2, 4, 6 only. So carbon doesn't have octet. How are we going to rectify that? Move lone pairs for a bond to carbon to get it to be octet. So you have lots of lone pairs here. Let's pick this one this time. Really doesn't matter which one you pick, right? And then show the result. The oxygen now only has 2 lone pairs. Here we still have the same situation, single bonded to hydrogen. So oxygen is still octet, right? 2, 4, 6, 8. And carbon now has obtained its octet, 2, 4, 6, 8. All right. So we good. So that's going to be our final structure. Okay. Now, we forgot to check, whether, the bonding pattern makes sense. But we can check it for here. Do you see how the bonding patterns earlier from that table? You see that it fits here, right? Carbon always likes to make 4 bonds, 1, 2, 3, 4, and has no lone pair. Oxygen likes to make 2 bonds and have what? 2 lone pairs, right? So it fits that pattern. Earlier we had this CH2, F2. It also fits the bonding pattern. Remember, 1, 2, 3, 4 bonds for carbon, no lone pairs. For fluorine, it likes to make 1 bond and has 3 lone pairs, right? So just a quick check for octet and your bonding patterns. It's going to help you be confident that you've drawn the right thing, right? So it's one of those cases where you don't need other people to tell you whether the structure is correct. You can actually check yourself first with octet, secondly is with the bonding pattern, right? Does it make sense? Okay. All right, I think you guys are good enough. We're gonna go to triple bonds. All right, triple bonds, N2. Let's do N2 first and then SCN. So N2 is 2 times 5, which is 10 valence electrons. Since it's only 2 nitrogens, that's easy. You don't have to really worry about central atoms, right? It's just 2. So draw the single bond between them. That's 2 electrons used. And 2 from 10, we have 8 electrons left. So 8, put around the nitrogen. To fulfill octet, right? Outside in. Doesn't matter to pick a nitrogen. Make it have octet first. That's 2, 4, 6. But now you only have 8 electrons. You use 6. So you can only put 2 here on the other nitrogen, and that's it, right? Well, we know this can't be the final structure because this has 8, but this does not. So that means, again, we need to move lone pairs down for another bond, right? A multiple bond. So when you move this lone pair down, we're going to have a double bonded nitrogen, where this nitrogen now has 2 lone pairs. This nitrogen still just has 1 lone pair, okay? Let's see if that made it better for this nitrogen. 2, 4, 6. Not good, right? This nitrogen's cool because it still has 2, 4, 6, 8, okay? But this nitrogen's still not good. So one more time, right? I'm going to take this lone pair down for a triple bond. Okay. Right? See how that works? Okay. Now this nitrogen is 2, 4, 6, 8 octet. Yay. This nitrogen 2, 4, 6, 8 octet. So we're good. That's going to be our final structure. We also check the bonding pattern too. And you notice it works. Nitrogen likes to make 3 bonds and have 1 lone pair, right? Just like we said earlier, just like we saw with that example we did on that table. So that's it. That's the structure for N2. Let's look at HCN. So that's gonna be 1 plus carbon is 4 plus nitrogen is 5. So that's 10 valence electrons. Central atom's gonna be carbon. Distribute the surrounding atoms evenly. Draw single bonds only. That's 4 electrons used. 4 from 10 is 6 electrons are left. And we're going to do from outside in. So that's 3 lone pairs on the nitrogen. Okay, and we've used up our 6. Okay, and so nitrogen 2, 4, 6, 8 has octet. Hydrogen's fine with 2. Carbon now has only 4, right? 2, 4. So we need to bring these 2 electrons down, or a lone pair, or a double bond, right? And now nitrogen only has 2 lone pairs. Over here stayed the same. But then we check with carbon. 2, 4, 6. Oh, not enough. So we'll do it one more time. Now we have a triple bond between carbon and nitrogen, where the nitrogen only has 1 lone pair. Okay. Check carbon for octet. 2, 4, 6, 8. Nitrogen 2, 4, 6, 8. Hydrogen with 2. Everybody's cool with octet. That's got to be our structure. And look at our bonding pattern. Hydrogen makes 1 bond. Carbon likes to make 4 bonds, no lone pair. Nitrogen likes to make 3 bonds and 1 lone pair. Okay. Let's graduate again. I'm going to show you guys now more complex, bigger molecules. Ones that have multiple central atoms. So H2O2, for example. So for H2O2, valence electron first, right? 2 times 1 plus 2 times 6. That's 14 valence electrons. Okay. Can we see that there are going to be 2 central atoms here? It's kind of obvious because there are 2 oxygens. Hydrogen can't be a central atom. Remember that? Right? So I would just put the 2 oxygens next to each other, knowing that that's my central atom. And then the rest of the steps should work the same way, right? The remaining, the surrounding atoms, which are 2 hydrogens, should be spread evenly around the central atoms, which means each oxygen gets 1 hydrogen, right? Because it's spread evenly. So just put a hydrogen next to the oxygen, right? So spreading evenly. And then the other steps are still the same, right? It's the beauty of these steps. They remain the same. Single bonds only between the central atoms and its surrounding atoms. And count, that's 3 bonds, so 6 electrons used. 6 from 14 is 8, so 8 electrons left. Okay. And we're gonna, again, doing outside in. Well, hydrogens don't need lone pairs, right? So put it on the oxygen. Just pick an oxygen and do it first, doesn't matter. So it was only making, it's already making 2 bonds. That's 2, 4. So only needs 2 lone pairs to get octet, right? 2, 4, 6, 8. And then this oxygen can get the other 4. 2, 4, 6, 8, right? So I've made 8 dots. I've put in my electrons, and everybody's happy with their octet. So that should be my structure. Okay. And just checking for the bonding patterns as well, right? This oxygen is making 2 bonds. It has 2 lone pairs. It's making 2 bonds, has 2 lone pairs. The hydrogen's just making 1 bond. Okay. Okay, and let's go to C2Cl6. That's our next example. Again, start with valence electrons. So 2 times 4 for carbon plus 6 times 7 for the chlorine. Right, so that's 42 plus 8, which is 50. Valence electrons, right? 6 times 7 is 42. 42 plus 8 is 50 valence electrons. Central atom or atoms, right? You can see that there's 2 carbons here, right? So I can clue you in that both of those are central, right? Because carbon is more to the left of the noble gas than chlorine. So I'll put the 2 carbons next to each other. And again, we're going to distribute the 6 chlorines evenly around the carbon, which means each carbon's going to get 3. Okay, makes sense, right? And then single bonds only from the carbon to the chlorine. Okay. And then count how many bonds you made. 1, 2, 3, 4, 5, 6, 7. That's 14 electrons used. From 50 minus 14, 36 electrons left. And so each chlorine is going to need 3, right? So three lone pairs. Yeah. So for the octet, right? Because it's already making one bond. So 3 lone pairs. 3 lone pairs. 3 lone pairs. 3 lone pairs. So how many dots have I made? 2, 4, 6. 6, 6, 18. Another 18 is 36. So that's it. That's all the dots I can put in there. And then I check for octet. I know the chlorines meet octet because I made them. So I just need to check the 2 carbons. 2, 4, 6, 8. 2, 4, 6, 8. So again, octet is checked. So that's my final structure. So you notice in the last 2 examples, the structure just fell in our lap. We didn't really have to do much, right? Just by following the steps. It's great. Okay, let's move on. CH3OH. Carbon, 4 valence electrons, plus 3 times 1 for the hydrogen, plus 6 for the oxygen, plus another 1 for the hydrogen. So for a total of 7 plus 7, 14 valence electrons. Okay, so let me tell you guys, give you a little hint here. Okay, anytime that you see sort of this chemical formula written out like this, it's trying to help you guys figure out the connectivity. Right, so when molecules get larger than this, it's gonna be hard to figure out what atoms is attached to what atom, right? And so a lot of times people write textbooks or authors will write and spell it out for you guys so that you know what's connected to what, right? So here's what I mean. It could have been written like this, CH4O, because there are 4 hydrogens. But if it was written like this, we wouldn't know connectivity, okay? It's more ambiguous. So if you spell it out like CH3OH, read it like a book from left to right, and you know what's going to be attached to what. So carbon, it's going to start with carbon, right? Because that's just central atom. Hydrogen cannot be, right? And then read H3. That means these 3 hydrogens will be attached to that carbon. Okay, so always be attached to the previous atom. So then you're like, oh, okay, that means I can attach my hydrogen like that. I'm leaving space because I know carbon makes 4 bonds, right? Carbon likes to make 4 bonds. So I use my bonding pattern to help me as well. That the oxygen is going to be there. That's why I made space for it, right? Because this oxygen is not going to be attached to the hydrogen because the hydrogen is already making the 1 bond with carbon. So that oxygen has to be attached to the carbon. And then this hydrogen is attached to that oxygen. Okay, so I get, I just read it out, spell it out, so I get the skeleton of it first, and then I continue with my steps and draw in the single bonds. 2, 4, 6, 8, 10 electrons are used. 4 electrons are left, right? And what I'm going to do? Outside in. Hydrogens don't need it, but the oxygen needs 4 for 2 pairs, 2, 4, 6, 8 to get that octet, right? And then I check the carbon, 2, 4, 6, 8. Right, so everybody has octet, and that's my structure, right? So notice how with the multiple central atoms with bigger structures, I can use how it's written out to help me get that structure right. And look at the bonding pattern. Carbon likes to make 4 bonds, no lone pair. Oxygen likes to make 2 bonds and 2 lone pairs. Hydrogen's always making 1 bond, right? Okay, let's move on. CH3, CH2, OH. So valence electrons, 4 plus 3 times 1 plus 4 plus 2 times 1 plus 6 plus 1 is equal to 7, 11, 13, so it's 20 total. Okay. Again, you see that it's spelled out like this, right? It could have been written as C2H6O, That's 6 oxygens total, right? But now it's like, I don't know what's connected to what. So when you see it written out like that, use it. So there's a carbon with 3 hydrogens attached. You know, carbon likes to make 4 bonds, so leave room for the next atom. The next one that's attached to carbon is this carbon. And now this carbon has 2 hydrogens attached to it. So put it here, right? Here's already attached to carbon. So it's going to attach to 2 hydrogens here. Leave room for it for the 4th bond to oxygen, right? And then on that oxygen, a hydrogen's attached to it. See? Again, right? Just going from left to right. So now single bonds everywhere. Okay. How many lines do we do? 2, 4, 6, 8, 10, 12, 14, 16. That's 1, 2, 8. So 16 electrons used from 20, 4 electrons left. Those 4 electrons are going to go on oxygen, right? It's not on the hydrogen. 2, 4, 6, 8. The oxygen has octet. Check carbons. 2, 4, 6, 8. This carbon, 2, 4, 6, 8. Okay. So we have octet. That's good. Okay. Let's check the bonding patterns as well, right? Carbon likes to make 1, 2, 3, 4 bonds without lone pairs. This carbon, 1, 2, 3, 4, 4 bonds without lone pair. This oxygen, 1, 2, 3, 1, 2 bonds, right? And 2 lone pairs. Okay. Fitting, and all the hydrogens making single bonds, right? It fits our bonding pattern. Okay, one last example for you guys. CH3, NH2. So we got 4 plus 3 times 1 plus 5 plus 2 times 1 is equal to 14. It's electrons. Okay, and again, it's spelled out for us as you can see. So there's a carbon with 3 hydrogens attached. Leave space for the 4th. The 4th one would be the next atom. Nitrogen is attached to that carbon. And then on the nitrogen, 2 hydrogens are attached to the nitrogen. So spreading it all out, it's already making a bond in this direction. So put the hydrogens here, right? So that it's evenly spread out, right? Then make the single bonds. Okay. 1, 2, 3, 4, 5, 6. That's 12 electrons used. And 2 electrons left. Okay, where are we going to put these 2 electrons? Well, the hydrogens are making a 1 bond, so they don't need it. Between the carbon and the nitrogen, which one's going to need it? Well, the carbon already has octet, right? 2, 4, 6, 8. So it's got to go on the nitrogen so that the nitrogen can have octet 2, 4, 6, 8. Right? So you can use that, right? See who needs octet? Let's put those last electrons there. So now that everybody has octet, right? We just checked 2, 4, 6, 8, 2, 4, 6, 8. Hydrogen's all singly bonded. So that's our final structure. Looking at the bonding patterns as well. Carbon making 4 bonds, 0 lone pair. Nitrogen likes to mix 3 bonds and has 1 lone pair. So we're good there as well. Okay, so that's it, guys. I hope I've given you plenty of examples for these Lewis structures. You guys go and crank out, on your own a few of those. And there should be plenty of them to do, especially in the homework. So you should be able to do all of those now. Okay, see you guys in the next video.